Hello and welcome to our Art Integrated project of maths. We will be demonstrating mathematical concepts with the help of Desmos calculator and GeoGebra. We have divided this project into 6 sections and we would be covering 5 different topics whose concepts can be illustrated with the help of mathematical calculators.
We will be going through equations of different powers on graph, basic forms of a graph, conic section in Desmos, parabolic curve, Seirpinski'sDesigns in GeoGebra, plots of all trigonometric functions, and some miscellaneous designs.
An equation of power 1 is called a linear equation, and the standard form of a linear equation is y is equal to ax plus b. Here is an example of a linear equation.
An equation of power 2 is called a quadratic equation, and the standard form of a quadratic equation is y equal to ax squared plus bx plus c.
And here is an example of a quadratic equation. An equation of power 3 is called a cubic equation, and the standard form of a cubic equation is y is equal to ax cubed plus bx squared plus cx plus d. Here is an example of a cubic equation.
An equation of power 4 is called a biquadratic equation, and the standard form of the biquadratic equation is y equal to ax power 4 plus bx power 3 plus cx power 2 plus dx plus e. Here is an example of a biquadratic equation.
And now we are going to look into some basic functions of a graph. There are many functions of a graph, some of which are linear function, square function, cube function, square root function, absolute value function, and reciprocal function, amongst the many others. Now let's head into the second topic of our math project, which is the conic sections. Let us explore the fascinating history of conic sections first. The conics was discovered by Menachmus, a Greek mathematician, tutor to Alexander the Great. They were conceived in an attempt to solve the 3 famous problems of trisecting the angle, duplicating the cube, and squaring the circle.
The conics are first defined as the intersection of a right circular cone of varying vertex angle, a plane perpendicular to an element of the cone. Depending the angle is less than, equal to, or greater than 90 degrees, we get an ellipse, parabola, or hyperbola respectively.
Circle. We all know what that is. It is all the points that are equidistant from the center, and that distance is the radius. Ellipse in layman's terms is kind of a squished circle. Circles are a special case of an ellipse.
And finally, for a circle. Now the basic formula for the construction of a circle in a graph is x squared plus y squared is equal to a, where a is a variable and it can be any number. But the formula of circles related to conic sections has a lot more application. For a circle of the conic sections, x minus h whole squared plus y minus k whole squared is equal to r squared, where the center of the circle is c, h, k. Here the variable h is responsible for the distance of the circle from the origin, k is responsible for the distance of the circle from the x-axis, and r acts as the radius of the circle. That is, as the value of r increases, the size of the circle increases. An ellipse is a set of points on a plane whose sum of the distances from 2 fixed points is constant. For any point on an ellipse, the sum of the distances from that point to each of the foci is some fixed value.
For an ellipse, x minus h the whole square by a square plus y minus k the whole square by p square equal to 1, where the ellipse is elongated along the x-axis, and x minus h the whole square by b square plus y minus k the whole square by a square equal to 1, where the ellipse is elongated along the y-axis.
A hyperbola is a set of all the points in a plane whose difference of distance from two fixed points is a constant. If the discriminant from the general form is greater than 0, it's a hyperbola. For any point on a hyperbola, it's the difference of the distances from the two foci that is fixed. This can also open leftwards and rightwards or upwards and downwards.
For a hyperbola, x minus h the whole square by a square minus y minus k the whole square by p square is equal to 1. When the hyperbola faces left and right, and y minus k the whole square by a square minus x minus h the whole square by p square is equal to 1, when the hyperbola faces up and down.
Parabola. A parabola is a curve formed by the set of all points in the plane. It is obtained by the intersection of the plane and a right circular cone when the plane is parallel to an element of the cone. A hyperbola is a conic section formed by intersecting a right circular cone with a plane at an angle such that both halves of the cone are intersected. So now that we have refurbished our knowledge on the conic sections, let us head into the designs.
Now let us see the formulas that make up these wonderful structures. For a parabola, x minus h whole square is equal to 4p y minus k, where if p is greater than 0, the parabola opens up, and if p is less than 0, the parabola opens down. And y minus k whole square is equal to 4p x minus h, where if p is greater than 0, the parabola opens right, and if p is less than 0, the parabola opens left. Now that we know about the physical properties of the conic section, let us look at some applications of it. Conic sections are used in many fields of study, particularly to describe shapes of the orbits of objects in space. Two massive objects in space that interact according to Newton's law of universal gravitation can move in orbits that are in the shape of conic sections. They could follow ellipses, parabola or hyperbolas depending on their properties. And that's it for the conic sections. Let us next see a more cosmic exploration of the parabolic curves.
Let us start with the basic parabola. A parabola is a curve where any point is at an equal distance from a fixed point and a fixed straight line. The parabola has a U-shaped figure.
As per our topic, we are concentrating on the parabolic curves. The main difference between the parabola and the parabolic curve is that parabolas are made by a curve and the parabolic curves are made by using straight lines to create the design.
The basic principle of this design is the creation of curved shapes. From the intersection of straight lines, all parabolic curves are created using the 1/4 inch marks. One of the easiest parabolic curves is the curving stitching.
Curve stitching is a form of parabolic curve where smooth curves are created through the use of straight lines. The process of curve stitching can be done with a piece of paper and a ruler or anything you can make a straight line with.
This can also be made using the Desmos graph. The basic curve design is achieved by connecting equally spaced points that are placed on two lines that meet at a 90-degree angle.
In the Desmos graph, we can use various formulas to create the parabolic curve. Here we can see the curve stitching drawn with the hand and also on Desmos graph.
To draw a parabolic curve, find graph paper. When you're learning, it is best to use graph paper. Put the paper so the long end is on the bottom top and the short ends on the side.
Using a ruler, draw a line from the top left square to the right of the bottom left cube. Make sure the line is straight. Using the ruler again, draw another line from the second to top left square and two from the bottom left corner.
Continue moving down on the left side and out on the bottom. Make sure you do not connect the wrong end to wrong end, as it is hard to erase. The interesting fact about these parabolic curves is that these can also be seen in Desmos graph.
Now we're going to look at some designs of parabolic curve that can be drawn by hand. And now we head on to the fourth topic of our math project, which is about Seirpinski's designs. We will explore about the history of Seirpinski and about these designs and how it has helped us in our lives. Let us first talk about the history of Seirpinski.
Vaclav Sierpinski was a Polish mathematician who interpreted his designs pattern in the mid-19th century. At the time, these designs existed and were used as decor before the work of Sierpinski came. So the art of Sierpinski has been used all around the world, but mostly seen in places like Italy.
But what makes these designs imply on mathematics? Every Sierpinski's design follows the mathematical idea of self-similarity. To explain it in a simple way, shapes will get repeated every now and then to create a basic but beautiful pattern. Now we go further into the topic. Although there are many Sierpinski's patterns, we will be exploring the two main common examples to understand the concept. The first and foremost design Sierpinski has interpreted was the Sierpinski's triangle.
This design is simple enough. A triangle formed over a triangle and over another triangle and seemingly goes on. The main purpose has always been for decoration, but its importance lies on its similar triangle. The way the triangle repeats itself is satisfying as it goes smaller and smaller, decreasing its area to half and perimeter to 1/4 as the triangles get smaller.
Creating a Sierpinski's triangle is easy and can be made in many ways, from drawing it to typing a code to create one. Many programs are specialized in creating beautiful pictures from the triangle itself. First, you need to create an equilateral triangle. Then divide it into 4 smaller equilateral triangles in which the triangle in the center must be removed. Repeat step 2 until you end up with a Sierpinski triangle.
Now we are heading on to the next design, being the Sierpinski's carpet. The Sierpinski's carpet is one of the Sierpinski's designs, which is made up of squares. As you can see from the name, it has been used as one of the designs for carpets and for decoration, but it also has its own real-life applications.
The Sierpinski's carpet has been used for Wi-Fi and mobile towers due to the abundant space useful for storing frequencies. It also provides balanced performance, which also helps for small mobile devices. The design also has its another form called a wireless sieve. Although they might be similar, the wireless sieve has a specific area, unlike the Sierpinski's carpet, which has a zero limiting area.
As simple as creating a Sierpinski's triangle, creating a Sierpinski's carpet is also simple too, by setting up a big square with its size decreasing the number of squares in a row multiplying. First, start with a large square. Second, divide the square into 9 smaller squares in 3 by 3 rows with the center square removed. Repeat step 2 until you end up with a Sierpinski's carpet.
And now we head on to the last section of our project, where we will be discussing about trigonometric functions on graphs.
Here we will be looking at the graphs of all 6 trigonometric functions.
Firstly, the sine function. The sine function has this beautiful up-down curve.
Next is the cosine function. Cosine is just like sine, but it starts at 1 and heads down. Thirdly, we have the tangent. The tangent function has a completely different shape. It goes between negative and positive infinity, crossing through 0 and at every pi radian.
Next is the cotangent function. The plot of the cotangent is similar to that of a tangent, but is the mirror image of the tangent function.
The graph of secant and cosecant are in the slide. They have a similar shape, but are different in terms of positioning.
Now we'll look at all of these in a Desmos graph.
Now we head on to the last section of our projects, where we will be going through a wide variety of designs that can be created using the Desmos calculator. The designs will include trigonometric concepts, concepts of polynomials and quadratic equations, element list, and many more.
that is our topic for the project all covered, and on this final note we conclude our presentation.